Hello and welcome to this video on determining the null space, or the kernel as some texts will call it, the null space and the nullity of a linear transformation. So in this video I'm going to define the null space of a linear transformation and what is the nullity of a linear transformation, and just go into several examples where we're given a linear transformation, so some transformation that satisfies the additivity and homogeneity properties. So I don't need to check those, and just go through those and find what is this null space of the transformation and what is the nullity of that same transformation. Alright. So what is the null space? Or again, like I said, and I'm not going to use this word too often, but you will see this in some textbooks. The null space of a linear transformation is sometimes referred to as the kernel of that linear transformation. Alright, so suppose we're given a transformation from vector space V into vector space W that is a linear transformation. Okay, so this satisfies the additivity and homogeneity properties that need to be satisfied, right, for a transformation to be linear. The null space, or kernel, of T is the set of all vectors V in the domain that have an image of the zero vector in the codomain. So it's all the vectors in the domain that map to the zero vector in the codomain. Another way to write this, the way to notate the null space of a transformation is just null of T, pretty much just like how you did the null space of a matrix, right? It was null of some matrix, but now it's a transformation name here. The null space of T is all the vectors V from the domain such that T of V equals 0. So we're basically just looking for all the solutions to this equation here. What are all the vectors that I can replace V with that have an image of 0, that give me an output of 0 when I apply the transformation T to it? Okay, and then what we're going to see here is that the null space of a transformation is a subspace of the domain V. Alright, so V is a vector space. This set of vectors here, all the vectors that map to the zero vector, this also forms a vector space. This would satisfy all 10 of the vector space axioms. But you can very quickly check if you want. This is non-empty for sure, because the zero vector would definitely, in a linear transformation, the zero vector of V will map to the zero vector of W. So the zero vector of V is in the null space, so it's non-empty. And then if you take two vectors that map to the zero vector in W and add them together, they will also map to the zero vector, so it's closed under addition. And if you take a vector that maps to 0, multiply it by a scalar, and here we're going to assume scalars are just from the field of real numbers, but they could be from any field, specified field, but we'll assume the real numbers are scalars here. If you take a vector that maps to the 0 vector and multiply it by a scalar, that scalar multiple will also map to the 0 vector, and this can all be shown through the properties of a linear transformation, right? The additivity and homogeneity properties. So it's closed under scalar multiplication as well, and it's a subset of V. So therefore, it's non-empty. It's closed under addition, closed under scalar multiplication. This is a subspace of V. All right. Okay, and then for the word nullity, and very similar to the nullity of a matrix that had come up in a previous video on null space and nullity of a matrix. The nullity of a linear transformation is the dimension of the null space, right? So this vector space here, the null space, whatever its dimension is is called the nullity of T, right? The nullity of the transformation. And to find the dimension, we just need to find a basis, right? And however many vectors are in that basis for the null space is what the nullity of that transformation will be. So I've already mentioned a couple times out loud here that the null space of T has similar notation and a similar definition to the null space of a matrix, doesn't it? And the nullity of a transformation has basically the same definition as the null space of a matrix. And if you recall, I'm hoping you recall, right, from previous videos if you've been watching, a linear transformation is a matrix transformation. You can write the output, or you should be able to represent the output of a linear transformation as a matrix multiplied by some input, by the input vector. Whether or not the input vector is in as a coordinate vector with respect to some basis, or just some vector from Euclidean space, every linear transformation should be able to be represented or expressed as a matrix transformation with a standard matrix, as has been discussed in previous videos again. So I've got this note here. The null space and nullity of a linear transformation will correspond or be related to the null space and nullity of the standard matrix for that transformation. Okay, so I'll show you, I'll work through both. So in these coming examples, I'll be giving myself a linear transformation. All right, so it's already linear, I don't need to check that. And I'm going to be finding the null space and nullity in one way, and then I'll find it in another way by using the standard matrix and show you how they give you the same results. Okay. Alright, so my first example, and every example in the rest of the video, has the following instructions. I'm asked to determine the null space and nullity of the linear transformation. So T is from, this is between Euclidean vector spaces R2 and R3. T takes a vector from R2 with components x1 and x2 and maps it to a vector from R3 with components x1 minus 2x2, 0, and the opposite of x1, or negative x1. Alright, so to find the null space of T, what I'm going to be looking for are vectors from the domain, right? I want to find all the vectors, and I'll call them, x. I know I called them v earlier, but whatever, it doesn't matter. Right? Find all the vectors from the domain. Right, the domain here is R2, such that t of x is equal to the 0 vector in R3. Right? So find every vector from the domain that maps to the 0 vector in the codomain. Right? Right, so what do these vectors look like? Right, the vectors from R2 look like this. I'll just call them the x1, x2 here. So x equals x1, x2. And we're looking at this equation. We're going to be solving this equation. Now t of x, if I called x x1, x2, and apply it here, the first component x1 minus 2x2. The second component will be 0. Again, I'm just doing the left side of the equation here. Third component, negative x1. And I want to know for what values of x1 and x2 can I use to give me the 0 vector as an output. Now the 0 vector here is the 0 vector in R3. So with 3 zeros as components. And this leads me to a system of equations. Right? Where in order for these vectors to be equal, their components have to be equal, right? So x1 minus 2x2 needs to be equal to 0. This second line, 0 equals 0, you can ignore this, right? This is like having a row of zeros in an augmented matrix for a system. This is always true, right? This is a true statement. You can ignore it, right? There's nothing to be done with that. There's nothing to be done with that line. So the only ones I'm focusing on are the first and third lines. So x1 minus 2x2 must be 0, and the opposite of x1, negative x1, must also be equal to 0. Right. And then, it's pretty obvious to me that from this third equation, x1 has to be 0. And if x1 is 0, let's put that in a circle, x1 has to be 0. And if x1 is 0, then the first equation, if I replace x1 with 0, you would just have negative 2x2 equals 0, and dividing both sides by negative 2x2 would have to be 0 as well. So it looks like the trivial solution where x1 and x2 are both 0, that looks like the only solution. All right, so the only solution to this system here looks like x1 equals 0, x2 equals 0. Okay, so that means that the null space of this transformation contains only the 0 vector, right? Only the vector x where x1 is 0 and x2 is 0. And I'll write that on the next page here. Okay, so the null space of this transformation is the set with only the 0 vector in it. Right, this is the only vector from the domain that would actually map to the 0 vector from the codomain. Okay, and you might recall, I've talked about this plenty in the past, this is a vector space, right? This is a subspace of R2, the 0 subspace, trivial subspace. Remember that vector space with only the 0 vector in it has an empty basis, a basis with no vectors in it, right? There's no set of linearly independent vectors that spans this space. So the nullity of T, the nullity is 0. Right? Again, I hope that rings a bell. I'm assuming you've seen this before, and I'm hoping you have in videos of mine if you've been following. The vector space with only the 0 vector in it has dimension 0. So therefore the nullity of T is 0. All right. Now, let me do this another way. Another way to do, find the null space and the nullity of a linear transformation is to write it as a matrix transformation, and then take a look at, and then find the corresponding null space and nullity of the standard matrix. All right, so just keep this in mind. We're going to get the same results again, all right, just a different way. All right, so same transformation. All right, so I'm starting off here again. Same transformation from R2 to R3, described this way. But I'm going to write this as, being that it's between Euclidean spaces, I don't have to change things to coordinates with respect to some standard basis. I can just leave things the way they are, and I can easily write this output as a matrix times the input vector. Now it's going to be a 3 by 2, right? Dimension of the codomain by the dimension of the domain matrix, right? It's going to be a 3 by 2 matrix. 3 row, 2 column. Down the first column go the coefficients of x1 in each of these components, so 1, 0, and -1. Down the second column will go the coefficients of x2 in these components, -2, and then 0, and then 0 again, and multiplied by, you know, the input vector, x1, x2. Right, and you can double check and multiply these two and make sure you get this 3 by 1 matrix back up here, but it should be good. Alright, and what I have now here, this 3 by 2 matrix, right, this is the standard matrix for T. And I'm going to call this standard matrix A. Alright, let's call this matrix A. Alright, 3 by 2. Now let's go and find the null space and nullity of A, and you'll see that it's basically the same as finding the, it's exactly the same actually in this case when you're between Euclidean spaces. It's exactly the same as finding the null space and nullity of the transformation. So say I want to find the null space of A. So that means we're trying to find vectors x equals, you know, x, one of these guys here again, the x1, x2, such that multiplying a by that vector will give me the 0 vector. I remember a times x equals 0. You're trying to solve this equation. Well, do you see that this is exactly the same? This here is exactly the same as t of x equals 0. Right? Because t of x, as we've seen, t of some vector is equal to a times that vector. Right? So we get the same null space. Now the way we would do it, right? Remember, we'd set up a little augmented matrix for this equation here. We'd have, again, here's matrix A, and then I'd imagine, right? You could write this, but you know, I put a bar here, and then you know, this needs to be equal to 0, this needs to be equal to 0, this needs to be equal to 0, right? x1 minus 2x2 needs to be equal to 0, 0 needs to be equal to 0, and negative x1 needs to be equal to 0. You could put the little bar and some zeros over here, you know, to make an augmented matrix for the system, right? And this would be the augmented matrix for this system, right? This system I wrote earlier. Say 1, -2, 0, 0, 0, 0, -1, 0, 0. Exactly the same as I have here. Now I don't need to write the column of zeros, because remember what we do is we put this into some echelon form, whether it be echelon form or reduced echelon form. And you know, when you're doing row operations, any column full of zeros is going to stay a column full of zeros. Alright, so I'm going to do this. Now I'm going to do this by hand. This one's not so much. I don't need to go to a calculator for this one to put this into reduced echelon form or reduced row echelon form. It's going to be a 3 by 2. Now I would just leave that one there, this pivot, add it to the third row. Alright, and that would make this 0 and then this -2. So that pivot's staying. The row of zeros I'm going to move to the bottom. I just move that to the bottom. And then this, you know, again, I add the first row and third row. I got 0, -2, and then that -2 becomes a new pivot, and I would make that into a 1, and then move it, you know, and then do some operation to get 0 above it. So hopefully you can see that this here would be the reduced row echelon form. And if you want to go to a calculator for this, fine. But you know, this 1, 0, 0, 1, 0, 0 rows, this is reduced row echelon form for that matrix. And remember, the first column represented coefficients of x1, right? The second column, coefficients of x2. So what these rows are saying is that x1 must be 0, right? Again, you're imagining the equals 0 on the other side here. The second row is saying that x2 must be 0. And then the third row is implying that 0 equals 0. Again, that's a true statement. You don't need to bother with that. That's okay. That's a true statement. Ignore it. as I said earlier. And then we get again our only solution. Right? So what we're seeing here is that the null space of A is the 0 vector, and that was exactly the same as the null space of T. Right? So the null space of A was just that set with the 0 vector, and the nullity of A, right, the nullity is just the dimension of the null space. And remember, I said it before, this vector space with only the 0 vector in it has a dimension of 0. And then we go back and say, okay, so the nullity of T, and then we just translate back. Now this is already a vector in R2. Remember I said earlier the null space will be a subspace of the domain. And the domain in this transformation is R2. And we're seeing that this is a vector from R2, so I don't need to change anything. This is the null space of T. Right, and the nullity doesn't change at all, right? There's nothing to change for the nullity. And the nullity of the transformation is the same as the nullity of the standard matrix, 0. Okay. Right. Right. The only time you're going to have to change is when, our domain is not a Euclidean space. And you'll see that in an example coming up. Okay, but you see how finding the null space of the standard matrix, leads me to the null space for the transformation. And the nullity of the standard matrix will be the same as the nullity of the transformation, right? Both of those are just the dimension of the null space. Great. All right, so let's keep that going. I'm going to do the same thing with every example. Here's another one. So again, I have a transformation T from R3 to R2. It's linear, right? It's a linear transformation, has additivity, homogeneity being satisfied. And it takes a vector from R3 with, say components x, y, z, sends it to this vector with two components, x minus y minus 2z for the first component, negative x plus 2y plus 3z for the second component. And the question is simply, for the null space, when is this output, what vectors give me an output that's the 0 vector in the codomain. Now the 0 vector in the codomain is just the 0, 0. So we're solving this, when is x minus y minus 2z, and then negative x plus 2y plus 3z, right? When is that equal to the 0 vector in R2, 0, 0? All right. So again, what I'm going to do here is solve a system, right? The corresponding system. The only way those are equal. Right, so again, this is t of some vector x equals the 0 vector. That's what I have written here. And the vector x is x, y, z. Has components x, y, and z. All right, so this is the system, x minus y minus 2z, negative x plus 2y plus 3z, and both of these being equal to 0. And can you see me writing this in matrix form? Right? It'll be a 2 by 3 matrix where down the first column I have coefficients of x, down the second column the coefficients of y, down the third column the coefficients of z, multiplied by the input vector, x, y, z. Right, so I could have done that up here as well. Right, said that this was equal to this, right, what I have here, and then this 2 by 3 matrix, right, this is the standard matrix for T. So again, I'll call it A, right, standard matrix A. And this needs to be equal to the 0 vector from the codomain, the 0 vector from R2. All right, so all I'm going to do is, you could write the augmented matrix But I'm going to take the standard matrix here and put it into reduced echelon form. Alright, so we'll go reduced echelon form or reduced row echelon form. Now it's only 2 rows, right? Not much going on here. Do you see I can keep that 1 as a pivot, and I add this to the next row, that would make 0 below it. And if I add these, if I add the first row to the second row would be 0, 1, 1. So then I have another pivot, there'd be a 1 here, which I would then just add to the first row, right? And get 0. And yeah, maybe if I do a little crossing out here actually. So I'll add these, make that a 0, make that a 1, make that a 1. And then I'll add these, make that a 0, make that a -1, and there we go. All right. So here we are. There's that matrix. And again, you're just imagining equals 0 over here if you're thinking an augmented matrix. Here's the matrix in reduced row echelon form. You have these pivot positions, these leading ones with the zeros below and above them. All right. And then, look for the pivots, right? The first column has a pivot, so x, remember these are coefficients of x, and the second column is a pivot. These are coefficients of y. X and y are my basic variables. And then the third column is not a pivot. All right, so z, right, these were coefficients of z. Z is free. All right. So like I like to do with my free variables, I'm going to replace them with some real number expression, right? Replace them with some other parameter. So you can keep it as z if you wish, but I like to do this, right? So I'm going to let z be equal to t, where t is just any real number I wish, right? So I can replace z with any number I want, right? Or now this variable t with any number I want, which is the same as z. And then from the first row, all right, from the first row we are seeing that x plus no y and then minus z or minus t is equal to 0, or x equals t. And then from the second row we're seeing that y plus z, so y plus t is equal to 0, leading me to y must be the opposite of t. Alright, so the solutions to this equation here, the vectors that'll be in the null space will look like the following. Alright, so the solutions to this look like this. X equals xyz, right? They're xyz, but x is the value of my free variable t. Y is the opposite of whatever I choose for t, and z is t. Or if you'd like, they all have the scalar t in common, t times the vector 1, -1, 1. So what we're seeing is that every solution to this equation here, right, every vector that maps to the 0 vector is a scalar multiple of 1, -1, 1. Alright, so the null space of the matrix, the null space of A, is the set of all the vectors that look like this. So some real number t multiplied by 1, -1, 1. Alright, such that t is some real number here. Now another way to state this, remember from a while back talking about spans and whatnot, this is the span of the set with just the vector 1, -1, 1 in it. Right, it's made up of all scalar multiples of 1, -1, 1. You can check this out, make sure this is true. Go back up to the rule here, and if I replace t with some number, like say, obviously 0 would be fine, 0, 0, 0 for x, y, and z would be good. But replace t with 1, replace x with 1, y with -1, z with 1, and both of these will be 0, both these components. Right. And so on. Just replace t with anything, and you'll get you'll get a vector that maps to the 0 vector in this transformation. And you see that this set with one vector would be a basis for this, right? This set with the vector 1, negative 1, 1 spans the space, obviously, right? Because this space is the span of it. And it's a single non-zero vector, so it's linearly independent, of course. So the nullity of the matrix is 1, right? The dimension of the null space. All right. Now, the null space of the matrix is a bunch of vectors from R3. The domain is R3, so this is also the same as the null space of the transformation. All right. So finally, I'll state the null space of the transformation, the null space of T, is the span of this set of with the vector 1, negative 1, 1 in it, right? So that just tells me that every scalar multiple of this vector maps to the 0 vector under this transformation. And the nullity of the transformation is always the same as the nullity of the standard matrix for that linear transformation. So the nullity of T is 1. Okay. Again, the dimension of the null space. How many vectors are in a basis for the null space, whatever. All right. Great. All right, so now we're getting into, so far the two examples we've seen have been between just Euclidean space, right? R2, R3, R3, R2, right? The next example I have is between a Euclidean space and a non-Euclidean space. All right, so, and if you recall, when we deal with non-Euclidean spaces, and we have a linear transformation as these are, in order to write a matrix transformation, in order to write out a standard matrix, I need to convert things to coordinates with respect to the standard basis. All right, so here I have R3, so I'm not going to convert that to coordinates. All right, that's a Euclidean space. It's already a column vector, vector A, B, C from R3 is my input. It's this P1, right? This is non-Euclidean, right? So what I'm going to do here is I'm going to write these, let's call this set C. Let's say set C is, make it like that, the standard basis for P1. Now remember, this is all polynomials of degree 1 or less. So every polynomial of degree 1 or less was some multiple of 1 plus some multiple of x, right? So the standard basis for P1 was just the set with 1 and x in it, or x and 1 if you put it in the other order, but I'm going to do 1, the constant, then the x to the first power. All right. So again, let me show you the two different ways we could do this. Find the null space of T. So we're trying to find, vectors from the domain, say x, which is this ABC here. And this is just represents, this is any vector from R3. Find those vectors such that T of x is equal to the 0 vector in P1. Now the 0 vector in P1 would just be 0 plus 0x, or the 0 polynomial. Right. So let's look at that equation. Right, let's write this out. T of x, if I apply ABC, that's a plus, and then the quantity b minus c times x. And the question is when this is equal to the 0 vector in P1 is 0 plus 0x. Now you could just say that that's 0, right? The 0 polynomial. Now the only way this is going to be happening, right? The only way that polynomials are equivalent is if the coefficients of like terms are the same. So this leads me to the following system, where you have a must be equal to 0. So there's the value of a that a needs to be. That's it clear as day. And b minus c, the coefficient of x, needs to be 0 as well. Oops, sorry, needs to be is 0, not x. Needs to be, the coefficients need to be equal. Right? B minus C needs to be 0 as well. So what I'm getting down here is that, A equals 0, and whatever I choose for B must be the same as what I choose for C. So any solutions to this system, right, any solutions to this system will look like this. X equals, A, B, C, but A must be 0 according to this. So 0 for the first component, A, and B must be equal to C. So I'll keep that as B and change C to B. Right? B and C, this is saying that the second and third component must be the same in order for this to actually work out, in order for you to have a vector that maps to the 0 vector. And look at this. Each of these have, B is just some real number, right? I can pull that out. That's a scalar. That's B times the vector 0, 1, 1. So what we're seeing here is that every vector in R3 that maps to the 0 polynomial, right, that maps to the 0 vector in P1, is a scalar multiple of the vector 0, 1, 1. All right, so we're getting here that the null space of T is this set of all values that all vectors that look like this. B times 0, 1, 1, where B is just some real number, but I mentioned this in the last example. This is just the span, right? The set of all scalar multiples of 0, 1, 1 here, the linear combinations of 0, 1, 1. This is just the span of the set with the vector 0, 1, 1 in it. And again, this would have dimension 1, right? Because clearly the set with 0, 1, 1 in it is a basis for this space. So the nullity of T is again equal to 1. Right, so there we go. That's one way to find it. All right. Now, the other way would be again to involve the standard matrix. All right, the standard matrix for this. So going back to the original, back up here. Now again, I mentioned that this, for non-Euclidean spaces like P1 or the set of 3x2 matrices or whatever, I'm going to involve look at what's the standard basis for that space, and then we're going to change things into coordinates. Right? And we're going to use coordinate vectors with respect to the standard basis. So coordinates relative to the standard bases. Now the input vector is from R3, so I'm just going to, it's already a column vector, I'm just going to leave it that way, A, B, C. It's for non-Euclidean spaces. Now this is still, these are also the coordinates with respect to the standard basis for R3, all right, 1, 0, 0, 0, 1, 0, and 0, 0, 1, but no need to write that for Euclidean space. Now here, A plus B minus C times x. What are the coordinates of this, or just the weights of the linear combination of 1 and x? All right, you have A times 1, the first standard basis vector. So the first coordinate is A, plus, and then B minus C is the coefficient of the second standard basis vector. So B minus C is the second coordinate in the coordinate vector with respect to basis C, and this is with respect to basis C. Maybe I should have called this something else because I'm seeing a bunch of C's here. I'll call this B then, I'm sorry. All right, so with respect to basis B, capital B there, right? Okay. And now that I have this, we can write this matrix, right? This is a 2x1 matrix. I can write this as a matrix multiplied by my input vector, ABC. Right, because this is a linear transformation. I mentioned it was linear, right? So you should be able to write or represent it as the output as a matrix times the input vector. So this is going to be a 2x3 matrix, right? Where down the first column are the coefficients of A, so 1 then 0, then the coefficients of B, 0 then 1, then the coefficients of C, 0 then negative 1, multiplied by that input vector, ABC. All right, so here's the standard matrix. this 2 by 3 matrix here. Here's the standard matrix for this transformation. And again, I'm going to call it A. And let's find the null space of A. So I'm going to take this matrix and put it into reduced row echelon form. Well, it already is. I'm just going to recopy it. It's already in reduced echelon form. Alright. And again, you're imagining now, right, we're setting this equal to 0. It should be equals 0, equals 0. We're trying to find A, B, C that make this product equal to, equal to the 0 vector. Equal to 0, 0 here. So yeah, what we're seeing is, pivot here. So A, pivot here in the second column. B, A and B are basic variables. And then, C is free. All right, the third column, which represents coefficients of C, doesn't have a pivot. Right? It doesn't have one of those leading ones. So I'm going to let C be equal to T, like I like to do, right, where T is any real number. And then from the first row, you're seeing that A has to be equal to 0. So no matter what, the value of A has to be equal to 0. From the second row, you're seeing that B, right, 1B, B minus C, so B minus T must be equal to 0 as well, so B must be equal to T. So now I have, every variable A, B, and C written in terms of this free variable T. And then the solutions to this, when is this going to be equal to the 0 vector, are, my A, B, C is going to be equal to, has to be equal to 0, T and T, and I can pull the T out, so T times the vector 0, 1, 1, which is exactly what we got earlier, right? Some scalar multiple of 0, 1, 1 will map to the 0 vector, right? We'll make this product here equal to the 0 vector. So the null space of A, right? The null space of A is, no, I should just write the span, right? The span of the set with the vector 0, 1, 1, right? It's all scalar multiples of the vector 0, 1, 1. And since these are vectors from R3 and the domain is R3, right, and the null space of a transformation is going to be a subspace of the domain, I don't need to change these. I don't need to change. These are vectors from the domain, so this is exactly what the null space of the transformation is, right? So the null space of the transformation is that span of the set with the vectors 0, 1, 1 in it. And the nullity of A, right, is just again the dimension of the null space, which again, is just the set with this one vector in it would be a basis for this. So the nullity is 1, and the nullity of the standard matrix is going to be the nullity of the transformation. Right, so same thing I got earlier, right? Exactly the same stuff I got earlier, right? Except I use I have B. But it's the span of 0, 1, 1, the set with 0, 1, 1, and the nullity is 1. Okay, now, so far so good, right? Finding these null spaces and nullities. My last example, I have 2 non-Euclidean vector spaces. All right, so this time I'm going to just jump to the coordinates and write the thing as a matrix, represent the transformation as a matrix transformation using coordinate vectors relative to the standard bases for these spaces. All right, so I'm going to call B the standard basis for my domain. All right, this is R 2 by 2. Remember, the standard basis, this is the set of 2 by 2 vectors with real number entries. Remember, the standard basis were those 2 by 2 matrices with exactly 1 1 and all the rest zeros. One entry is a 1 and all the other entries are zeros. So there are 4 of these, right? The dimension of R 2 by 2 is 4. So here is the standard basis for the domain. And I'm going to let's call this, instead of C, because I got some C's written up here, How about B prime? All right, or some other letter if you want, but just know that B and B prime aren't the same thing. And here, we'll call this the standard basis for P2. Now, P2 was the set of polynomials of degree 2 or less. So those are all multiples of 1 plus multiples of x plus multiples of x squared, right? So the standard basis for P2 has these three vectors, right? This is dimension 3, 1, x, and x squared. All right. So what I'm going to do now is take this transformation the way it looks and convert it to where my vectors, my input vector and my output vector, are written as coordinate vectors. All right, so again, I'll just change everything to coordinates. So I have T of, and then my input is this 2 by 2 matrix, right, with A, B, C, D as the entries. I'm going to write this as a coordinate vector with respect to basis B. So you see how this, to make this matrix, I'd have to have A of the first one plus B of the second one from the standard basis plus C of the third one plus D of the fourth one. So A of the first, B of the second, C of the third, D of the fourth. There's the coordinate vector for my input matrix there. And then over here I'm going to have a coordinate vector with respect to basis B prime, right, with respect to the standard basis for the codomain P2. And I'm trying to, how is this written as a linear combination of these three? Well, it's B times 1 plus 2C times x plus 3D times x squared. So the weights, right, the coefficients are B, 2C, 3D in that order. So those are the components of my vector, B, 2C, and 3D. Right, it's a 3 by 1 coordinate vector. All right, and I've mentioned, right, these are all linear transformations already, right, so I don't need to check for that. And since they're linear, I should be able to express this now, this coordinate vector representation. I should be able to express the output as a matrix times the input vector, A, B, C, D. All right, so this is going to be, this dimension 3 here, dimension 4. This should be a 3 by 4 matrix, right? Down the first column, the coefficients of A in these, well, it's all zeros. There's no A in any of those. Down the second column, oops, only 3 of them. I said 3 by 4, didn't I? All right, let's make that an edge of the matrix down there. All right, three rows, 4 columns, right? So 0, 0, 0, 0, 0, 0. Down the second column, the coefficients of B in these, 1, 0, 0. Then down the third column, the coefficients of C, 0, 2, 0. And then down the fourth column, the coefficients of D, 0, 0, 3. And so there's your 3 by 4 matrix multiplied by the input vector, the A, B, C, D. There are these coordinates with respect to the standard basis for the domain B. And you can go ahead and double check, multiply these two matrices, and you'd get this 3 by 4 times a 4 by 1 would be this 3 by 1. You can double check and see that it works. Okay, and then if I were to put this, now it's already in echelon form, right? The standard matrix here. This is already, so again, here's the standard matrix. I'll call it A. Now, like I said, it's already in echelon form. It's not in reduced echelon form because I just need to, all I would need to do is make these into ones, which I could do on the next page. All right. But you see how there, every row has the first non-zero entry has zeros below it, right? First non-zero entry has zeros below it. First non-zero entry has zeros below it. So it's in echelon form. So let me find the null space of A. All right, again, I'm calling this matrix A. All right, so for the null space of A, I'm going to put this into reduced echelon. Again, not a huge deal, but I put this into reduced echelon form. All I would need to do is change these into ones, multiply the second row by a half, the third row by a third. And again, you're imagining the zeros on the other side, right? I'm trying to figure out what A, B, C, and D need to be. Well, what this input matrix needs to be. I'm trying to find these vectors so that this product gives me the 0 vector, 0, 0, 0 over here. All right, well, looking at this echelon form, or even reduced echelon form, you see how the pivots, right, these leading ones, are in these last three columns. So I'm seeing that B, C, and D are basic. The first column, right, which corresponded to coefficients of A, that's not a pivot column. A is free. So I'm going to let A be replaced by the letter T, right, where T is any real number. You don't have to, again. I just prefer it. I don't know why. All right, it's just a preference. You can leave it as A as you wish, if you wish. And then what we're seeing from each of these rows here is that, B has to be 0. B has to be 0. C has to be 0. And D has to be 0. But A can be anything I want. All right, A can be anything I want. So, the null space of A, the null space of the matrix A. Well, first let me state the solutions, sorry. So the solutions of this here, when I set this equal to the 0 vector, this product, my ABCD, right, that ABCD, which again were coordinates with respect to basis B, must be equal to, A can be T, and then B and C and D have to be 0. Right? A can be anything I want. And I can pull the T out, T times 1, 0, 0, 0. And again, these are coordinates with respect to basis B. All right, so the null space of A is made up of all the scalar multiples of this vector 1, 0, 0, 1, 0, 0, 0. So the null space of A is the span of the vector 1, 0, 0, 0. All right, all scalar multiples of that. And therefore the nullity of A is again 1. Now, so far in the examples I've shown, the nullity has been 0 or 1. Just know that, and you've seen hopefully a video on null space or read about null space of matrices before. Just know that the nullity of a matrix, the nullity of a transformation can be higher than 1. All right, you can have a dimension 2 null space, dimension 3 null space, etc. Just please know that. Just don't go based on all. These examples aren't all the examples in the world. So then I translate this to T. All right, because remember these are the coordinates. Right, when I say the vector 1, 0, 0, 0, I can't say that's the null space of T. And the reason is, remember, the null space of a transformation is all vectors from the domain that map to the 0 vector of the codomain. This vector is not in that. 1, 0, 0, 0 is in R4. Right, this is in R4, right, not R2 by 2. But I can translate it, right? These are the coordinates in R4. I should say the coordinates in R4. But they're not a vector in R2 by 2. But what I do is just translate back, right? Remember the standard basis for R2 by 2 was this thing? So the null space of the transformation is not the span of this, vector from R4, but the span of, and then what does this vector represent in R2 by 2? So remember, these are coordinates with respect to basis B, so I have 1 of the first vector and then 0 of the other 3. So it's just that first matrix there in the standard basis, 1, 0, 0, 0 there. That. All right. Here's the null space of the transformation. So you see what I was saying earlier about how the null space of the standard matrix corresponds to or relates to the null space of the transformation. Just know that, if the domain is not Euclidean, the null space of the matrix, you'll have to translate that back so that you have vectors from the domain of the actual transformation. All right. So every multiple of this vector, every multiple of 1, 0, 0, 0 here would map to the 0 polynomial in P2. You could try that out. Take 1, 0, 0, 0, plug it in here. You'd get the 0, 0 plus 0 plus 0. Put in 2, 0, 0, 0. All right, plug in that matrix, you'd get 0 plus 0 plus 0. Yeah, every single vector, every single matrix that's a multiple of this one would map to the 0 polynomial in P2 in this transformation. And as I mentioned before, the nullity of the standard matrix is the same as the nullity of the transformation, right? So the nullity of the transformation is also 1, right? Because the dimension of the null space is 1, right? You have a basis with one matrix in it, one vector. So yeah, that's it might be a bit tricky, but just be certain that, you know, again, I'll say it again, if the domain is not a Euclidean space, don't just write the null space of the standard matrix as the null space of the transformation. Right? They're not exactly the same, but they can be translated into one another. Right? They correspond to one another. They're very closely related. The null space of the matrix, the standard matrix, will be some coordinate vector that looks like it's in R for some Euclidean space. And then just translate those coordinates back into, you know, what are the vectors from the domain of the transformation that would map to the 0 vector of the codomain, right? So just be careful with that. All right. So hopefully that's simple enough. If you recall finding the null space and nullity of a matrix, that's going to help out quite a bit here, because if you're given a linear transformation between any vector spaces, you should be able to express that transformation as a matrix transformation, right, with some matrix times the input vector as the output. Then you take that standard matrix, put it into some row echelon form or reduced row echelon form, identify your basic and free variables, and just again you're imagining the equals 0 equals 0 equals 0 equals 0 on the other side, right? And just find all the solutions, all the vectors that would map to the 0 vector, and there you go. You have the null space of the matrix. And then if the domain is not Euclidean, if the domain is Euclidean, then the null space of the matrix and the null space of the transformation are the same. You're fine. If the domain of the transformation is not Euclidean, then you're going to have to take the null space vectors of the matrix. Those would be coordinate vectors with respect to the standard basis of the domain of the transformation, and translate those back, into what are vectors from the actual domain that would map to the 0 vector, like I did in this last example from here to here, right? All right. So I hope you enjoy practicing problems on null space and nullity of a transformation, and thank you very much for watching.